Tier 4 is currently the last tier of a number of years starting in 1996 that we'll be getting, and frankly, we probably won't ever hear anything called a Tier 5. There may be other things coming along, but this will probably be it. And what I want to talk about today, I'm going to talk about kind of a high-level overview of the Tier 4 changes to start with, and then get a little bit more into the meat of it. What are the regulations for Tier 4? What are the technical solutions that people are using for Tier 4? A little bit of a advertisement here for Cummins. I will show you what the Tier 4 products are that we're coming out with, and how Tier 4 is going to impact the customer. So, let's see here. Okay. Before I get into that, though, I want to share with you a clip of some of the early years of after-treatment. You know, when we started getting into after-treatment, and we got into it on the automotive side way before we did on the industrial side. Engineers, our engineers went out and see what's going on, what's been done in the past and so forth. And they came up with this clip that they found. And it's a clip from the 60s, actually, which shows that there was actually some after-treatment work going on way back in the 60s. Now, I'll apologize, it's not the best thing to see, and maybe we can turn the lights down for this clip and then we can bring them back up again. Because the clip is kind of old, but I think you'll get the general idea.
How do you do, Granny?
It's the small goober! Everybody out there!
I done invented a small device small enough to fit on any car. What? I never saw one that small. Why, that's amazing. I tested it. It works. This is without my device, and this here is with it. Handled it completely. What a breakthrough. I'll pull the truck up front and demonstrate it for you. We'll make a fortune.
Now, wait, Mr. Drysdale. If it's good for folks, we'll want to give it to the country.
Yeah?
Well, that's wonderful.
Okay, Mr. Tinsley. Ready to put my device on the truck.
Ah, you're a genius. Building a workable device this small.
Oh, the device were nothing. The real problem was making the filter.
Filter? That's the filter?
Yeah, you ought to see it before I got it down the side.
Great Scott.
The Beverly Hillbilly. Welcome back now, dear.
Okay, well, it's absolutely perfect that that happened in California. And, I really liked Uncle Jed until I found out he was the one that donated all the money to start CARB. They've been a pain ever since. But with that, kind of a high-level overview, regulations for clean air, Tier 4 interim starts in 2011, Tier 4 final starts in 2014. More could follow, probably not in the form of a tier, but other things that we'll be looking at, and I'll share some of that with you towards the end of the presentation. The significance here, though, is that this is an order of magnitude reduction in both particulates and NOx, nitrogen oxides, compared to previous tiers. Tier 4 interim for industrial or off-highway equipment is equivalent to the last two on-highway emissions, 2002 and 2006. Put both of those together, and that's what we're doing at Tier 4 interim. Tier 4 final, what happens in 2014 is going to be the off-highway equivalent to the on-highway event that just happened here starting January this year. You keep hearing rumors that the government's going to defer this stuff. It ain't going to happen. It just isn't going to happen. There's too much money and everything invested by engine manufacturers, equipment manufacturers, to just defer it for a couple, 2-3 years. We have seen them defer in Japan for about 10 months. They're using the current world economy as a reason for that. But you're not going to see it here in the U.S. So the impact of Tier 4, actually you're going to see the same or better machine operating capabilities. We fully expect to see better capabilities in machine operation, and I'll cover that in more detail later. There's going to be changes in the fuels used, lubrication, and there's going to be a few different additional maintenance practices that will have to be incorporated. But again, there's also an operating cost savings opportunity in the form of better fuel economy. It's been an interesting ride. There's a lot of work that goes into reducing emissions, and you would think with all that work to continue getting strides in better fuel economy. It's been happening every single tier level that we've done off-highway. We've been able to get better fuel economy. And I say that as, in general, the industry, all the different engine manufacturers have done. And then a lot of what I'm talking about today applies to them. And I'll mention some specifics here and there, but it's not just Cummins that's doing all this work. So how do we prepare for it? Well, we need to understand it. We need to gather the knowledge as we read and learn about it, and need to plan and then act on it. So let's go. What's the reason for all these? Well, obviously the improving air quality is the main reason for all the emissions. There's a lot of reasons, but I wanted to show you that this National Ambient Air Quality Standards that the government set up a number of years ago, they cover 6 different pollutants, and you can read them right there. The 2 that are the hardest to meet for diesel engines are the NOx and the particulates, particulate matter and nitrogen dioxide. Interestingly, for these local air quality, ambient air quality, the states are responsible for compliance. And if you look at the biggest area, surprise, surprise, it's California. They've got a lot of problems out there, and they're continuing to work at them. But boy, it's tough. It's really tough for them to get there. If you take a look on a worldwide basis, in 2008, construction mag, which includes a myriad of different types of applications, where they're regulated and where they're not, you can see North America, Europe, I think Japan over there, are all Tier 3 in 2008. There's a few Tier 2s and some Tier 1s, but there's a good portion of the world that's totally unregulated in 2008. When you go to 2011, next year, the main ones, North America, Europe, Japan, have moved to Tier 4. India has moved to Tier 3. Soviets are still at Tier 2. China is Tier 2. Brazil, the first time we've seen something down in South America, is going to be at a Tier 2 type of level. But still, an awful lot of the world is just totally unregulated. Now, as I said, there's a 2-phase introduction for Tier 4. It's an interim and a final. The Tier 4 is focused on particulate matter and NOx emissions. The introduction of these regulations varies by horsepower band or bracket, and I'll show you what I mean by that in a slide or two, but the emissions are split up in different horsepower brackets, if you will, and those are spread out over different years. And fortunately for us, U.S., Canada, EU, Japan are all going to be broadly aligned, so it appears now that we'll be able to essentially make one engine, and those regulations, that engine will fit all those regulations. We won't have to build different engines for different parts of the world. At least are regulated. Those that aren't regulated, that's a different story. Okay, the phase-in. As you can see, this is EPA and EU. There's the Japanese ones, but it tends to clutter up the page a lot more if you don't. But we are split up. These are your horsepower brackets right here that I was talking about. So different times for different horsepower brackets. What we're going to talk about primarily today is the 174 to 751. The reason we're going to talk about that is those regulations are the most stringent regulations of any horsepower bracket up there. You probably, you pretty much have to throw everything but the kitchen sink at that one to get it done. And as you go below that or above that, the regulations aren't as stringent. So you may not see quite the same solutions for those In fact, I know you won't see the same solutions, and those solutions typically aren't as expensive because they aren't as, technology, they aren't as far advanced as what you need for the 174 to 751. And the one other point I want to make here is that greater than 751 horsepower, the U.S., and that includes Canada because they just kind of copy what we do, is the only place in the world today that has emission regulations for above 751 horsepower. Now, we hear conversations that Europe is kind of looking at them, but we've seen nothing in writing or in concrete yet. So this is the only place in the world that has regulations above that. Take a look at what this really means to us. Tier 1, right there, represents that whole box. I'm sorry, Tier 2. Tier 3, they reduce the NOx, and as we go into Tier 4 now, NOx is being reduced 45% lower for Tier 4 interim, and particulate is actually being reduced 90% for Tier 4 interim. And then for Tier 4 final, we get another 45% drop in NOx. So Tier 4 interim, we're doing half the NOx and all the particulates. Tier 4 final, we're doing the other half of the NOx. That's how it works out. The other thing that you want to notice on this slide is that it becomes very, very similar to what's happening on highway in the U.S. And what that does is it really drives a technology convergence. So if you kind of look at what's been going on highway and the technology that's been used there on highway to hit the different emissions levels, you're seeing the same thing happen just about one step back. What we're seeing in 2010 is what we're seeing in 2011 was 2007. Tier 4 interim will be like what we're seeing just kick off this year in 2010 automotive. Here's one of the things that the engineers have to figure out, and it's not an easy thing to do. Pollutants going up here, increase here, combustion temperatures increasing. If you increase combustion temperatures, that reduces the particulates, but it increases the NOx. Vice versa, if you lower, that decreases NOx, but increases particulates. So you always have to deal with that, and it's quite a balancing act to get it just right. So kind of keep that in mind as we go through the rest of it. What I'm going to talk about now here is what are the regulations and so on, how we're going to kind of meet them. One of the things, one of the things that is today is that we didn't have before is for Tier 4 interim, the engine manufacturers are now responsible for tailpipe out emissions. Previous to that, they were responsible for emissions out of the turbo, just out of the turbo, and then beyond that, they weren't responsible. So now that means that the engine manufacturers have to take their packages, in this case an engine, particulate filter, those all have to be put together as one, and the system has to be certified. And it gets to be kind of crazy because if the engine and the after treatment ship separately, there's different things we have to do with the OEM as opposed to if they're shipped together, and there's all sorts of crazy regulations, but you get kind of used to that dealing with the government. They have some crazy things that they do all the time. Another thing that's changed for Tier 4 as far as regulations is up until Tier 4, industrial was just a steady state 8-mode test, and that's what is represented right here. There's 8 different points here, and we would bring the engine to that point, measure the emissions, and then we'd put them all together, and they each have a factor of how much they're included, like 10%, 10%, 15%, etc. And that's the emissions you emit. Well, that's been okay up until now, but now the government has thrown a transient cycle test on us that we have to pass as well. The automotive guys have been doing that for several years now. I think the last 3 regulations they've had a transient test cycle they have to go through. But this is the first time for the industrial to do the transient test. So it's a much tougher test to pass than this. So we're still doing this. We've added that. This right here, what it really is tough to do is to pass particulates. And particulates are just essentially unburned carbon. And what happens in most cases, and the reason why it's tough to pass, is that you have all these acceleration spikes. And it's typical in any internal combustion engine, diesel in particular, is that you can put the fuel in a whole lot faster than you can get enough air in to burn it. And that's why you have these particulates, unburned fuel. And the faster you can get the air in, the quicker you get a good mixture of air to fuel, and therefore your particulates you don't have as many particulates. So that's a pretty tough one to do. Another thing that we're going to have for Tier 4 is ultra-low sulfur fuel. We've been getting lower fuel. It was kind of the average up until June of 2007 for industrial. It's been up in the 2,300. In June of 2000, it dropped to 500. This is already there in 07 because of the automotive. They needed it prior to that. They needed it in 2002. And now the 15 parts per million, the ultra-low sulfur fuel, is it's been around since 2007 because automotive needed it. So it's out there. Infrastructure may not be aimed properly at industrial right now to get you that stuff to a site or something like that, but it's certainly for the on-highway trucks, it's readily available. And this right now is what they started in 2010. The fuel companies have been putting it out since, maybe last August. You're starting to see it show up at the pump at some of the truck stops, but most often, I would say probably 89% of the truck stops have that stuff now. You might find some on some off two-lane roads, but any of the major interstates and stuff, you have no problem finding that. Still going to be a little bit hard to find for now for off-highway, but that's going to happen pretty quick once we get going. It's just a matter of getting the oil companies to be shipping, bringing it into you versus just taking it to a truck stop somewhere. And if you look at Europe, roughly the same thing. They're at 10 parts per million, but what's a couple parts per million between friends? Same thing with Japan. We're down around 10 parts per million, I mean. One of the things I wanted to talk about separate from particulates is sulfur dioxide emissions. One of the reasons why we're taking the sulfur out of the fuel is to reduce sulfur dioxide emissions. That's just one of the reasons. It is not consumed during engine combustion. So it's just kind of a pass-through that comes through and it goes out in the atmosphere. This is contributes to ambient and particulates and regional haze. Another thing that SO2 does is it dissolves in water vapor to form acid rain. The problem with it when you get into the diesel engine is it impairs the operation of the after-treatment system and it plugs the particulate filters. Low sulfur fuel is there, it's 15 parts per million. Interesting, this acid rain, that was another reason similar to why we had to get rid of it for when we went to Cooley GR Automotive in 2002. When you cool that exhaust gas that you're recirculating back into the cylinder in Cooley GR, it runs into water vapor. And as it combines, you've created sulfuric acid. Now, that is not good inside of an engine. It attacks all sorts of stuff. So the only way you can get rid of it is to take the sulfur out. The other nice thing it did is when you got rid of that, you know how you had that funny exhaust smell coming out of diesels? Well, when we took the sulfur out, that stuff all but went away. You just don't smell it anymore. So another good reason to get rid of it. This is a map of the world that shows what type of fuels we have around the world today. This gray area right here and a little bit there and blue, you're talking essentially 50 and below parts per million. But there's a lot of parts of the world that are above 500 and above. And that's not going to work in today's Tier 4 or on-highway type emission vehicles. It won't work. It'll plug up the particulate filters. It will cause some issues with sulfuric acid in the engines, but it's not going to work. So you have to look at not only what goes into the regulated world, but what kind of engines you ship to the unregulated world. If you ship a Tier 4 engine into the unregulated world, it's just not going to work. Another thing that we've got to look at now that we didn't in the past, crankcase emissions. For Tier 4, that has to be part of the equation in figuring out emissions. Prior to Tier 4, we didn't have to worry about it. So there's several different ways of controlling those emissions. Filters or closed loop systems where it doesn't get out into the atmosphere, but we'll talk a little bit more about that. But again, just one more thing we got to worry about when we're figuring out emissions and getting these engines to meet emissions. So we've got to do all that stuff and somehow end up at the end of the day with an engine that meets the emissions. So how do we do that? First of all, a little terminology. We work on a lot of acronyms, so I'll clear up some of it now, and if there's something that shows up and you don't understand it, raise your hand and I'll explain it to you. DPF is a diesel particulate filter. DOC is a diesel oxidation catalyst. Soot is just carbon from incomplete combustion. Ash is incombustible materials that comes out of the lube oil. Ash in lube oil is used as to offset acid buildup. So it's a base type material that will offset acid buildup. Regeneration, that's a process where we remove the soot from a particulate filter through an oxidation process. SCR is selective catalytic converter, and DEF is diesel exhaust fluid. Is there anybody from Europe here? Well, the European version of DEF is called AdBlue. You may have heard that name floating around. I think some of the European cars that are here in the U.S. that run diesels talk about AdBlue. It's the same thing. I guess we just had different marketing folks that came up with different names, that's all. So the learning curve on technology, if you look at on-highway, back in before 90s, mechanical fuel systems, and in the early 90s we started looking at electronic fuel systems, and by about 94 it was all electronic. From jacket water after cooling to charge air cooling, started there and then went on. And in 2002, I think, we started looking at exhaust gas recirculation and variable geometry turbos. And in 27, I think it was, after treatment. From off-highway, everything was just set back a few years, if you will. Mechanical, we didn't start doing electronic until the early 2000s. And we're now, I think, from about 2006 onward, we pretty much have all electronic engines, except for that real low horsepower range. But certainly in the 174 to 751. Jacket water after cooling kind of starting to convert to charge air cooling. And then 2011, we're looking at exhaust gas recirculation along with variable geometry turbos and after treatment at the same time. So you can see these two things that we're doing at the same time, automotive did them here and then here, these two different times. But a lot of miles that we've done personally, our company, 7 billion miles have accumulated on Cummins engines in over-the-road trucks. So the technology here and the technology here are essentially the same. We've got a lot of experience from up here that we can transfer down here. And other engine manufacturers, I mean, to some extent, some have more than others, but I would venture to say that we probably got more than anybody, particularly when CAT dropped out of the automotive world back in 2007. They no longer were gaining that type of experience. So we've got to, for Tier 4, we need to kind of step to the next level of system integration to make all this thing work and work well. First, starting with the engines, we now go from air intake, variable geometry turbos, high pressure common rail, which is advanced fuel systems, integrated controls in our ECMs, exhaust after treatment. All of this is now controlled by the ECM on the engine. So it's all integrated as one package, which makes sense when you think back about the EPA said, well, we have to certify it as one package, so the best thing to do then is to integrate it all as one package. This is a chart that shows the different types of technology that you can use to resolve emissions. In cylinder, I think all the engine manufacturers are doing that to one extent or another. We actually have software programs that can simulate in cylinder, and we can do a lot of what-ifs on a computer before we actually take it to the test cell. There's not very many other engine manufacturers that can do that, but they can probably do partially. Cooled EGR, I think all of them have one form or another there. Variable geometry turbos, I'll get to in a minute, but there's different types of those that different engine manufacturers use. A NOx absorber, that's pretty unique to us, and that was what we put on the Dodge pickup truck in 2007, along with the other, this and this, that allowed it to meet 2010 emissions in 2007. I don't know of anybody else using a NOx absorber. It's something that we helped develop. So, but SCR, there's something we've been using that since 2004. Europe has a little bit different regulations than we do. They're off just a little bit, particularly on the on-highway side, a lot closer on the off-highway. But what resulted there was that they had also a very good infrastructure in Europe for their AdBlue, if you will. So they kind of went SCR early on the automotive side, and so we've been supplying engines over there since 2004 using SCR technology, and now we're using SCR technology as an add-on to the DPF, diesel particulate, and the EGR technology here in the U.S. So we've got a lot of experience with SCR because of that. Tier 4 interim, cooled EGR and variable geometry turbos and PM after treatment. Those are the two things that we're going to be using. And most of the other engine manufacturers are using that. There's a few that have opted to use SCR. For the most part, those are European engine manufacturers. So, if you take the current Tier 3 product, it's a proven platform. It's been around for a long time. The technology that we used for Tier 3 was high-pressure common rail, pretty common for the engine manufacturers off-highway Tier 3. Electronics, again, pretty common. And in-cylinder advanced combustion technology. That's not quite as common. That's what made up Tier 3. To that, we are now adding cooled EGR. In Tier 3, there were some engine manufacturers that used cooled EGR as part of their solution. So they've been using that a little bit longer. Variable geometry turbos, crankcase filters, that's how we take care of the crankcase, and Cummins particulate filter. All of this is stuff that most engine manufacturers are using in one form or another. They may use a little bit different formula than we are, but they're all using some of this stuff. So, I'm sorry, yes? No. There's so many things that are different that the cost of putting a kit together would probably be more expensive than just buying an engine. Now, I say that, and I'm talking about just the engine portion of it, okay? The after treatment is something, it probably wouldn't work because you don't have an ECM that hooks to it to make it work on a Tier 3 engine. It's a new ECM, so that would be, but the engine itself, we're taking a Tier 3 engine, we're adding cooled EGR and variable geometry turbos, both of which are managed by the ECM. And then we're adding after treatment, again managed by the ECM. And the stuff, it's just not cheap. and to put it together, it would be tough. It really would be. So let's talk about diesel particulate filters, how they work. Essentially, there's an oxidation catalyst in the front part here, and what we call a wall flow particulate filter back here. And really what that does is it traps those particles of soot. Any one of these lines that's open on this side or holes, it's closed on the other side, and vice versa. The one next to it is closed on this side, then open on that side. So it forces all of the exhaust gases to go through those walls, and that's how we get them to trap it. Now, as that builds up, the soot builds up in these walls, we have, you don't see them here, but there's actual pressure sensors in there, and we see a increase in back pressure from that. The ECM says, okay, it's time to do a regeneration. Most of the time, it just does real passive, but occasionally if it gets too much of a back pressure, then it causes an active. So, but it's still all taken care of right in here. So regenerations, the passive side, which is it does most of the time, the carbon or soot is converted into carbon dioxide at a faster rate than the filter is collecting carbon. And the exhaust goes through that diesel oxidation catalyst, it oxidizes, and it comes in there, and then with the heat, it oxidizes again and pulls that carbon together, CO2, and put it out the back. And it's a self-cleaning system. It runs naturally, takes care of itself. You got to have a certain amount of temperature in here to make that happen, somewhere around 500 degrees to 600 degrees to make this natural happen, and that's not hard to do in most cases. Some of the duty cycles that we see on some of the ground support equipment wouldn't justify that right now, but there's things that can be done to help that as well. This is active, so when the ECM sees that the filter is loading up with carbon and it gets to a delta P to a point where the ECM knows that, okay, we're not going to be able to do passive, then it does a active regeneration. And in active regeneration, the exhaust gas is coming in like it normally would and doing all the things it does. But in the exhaust stroke of the engine, we add a little extra fuel at the end of the exhaust stroke, and that comes in and hits the diesel oxidation catalyst, and it has a chemical reaction, and it creates a lot more heat. And so the heat buildup comes up pretty fast, and then that goes on through and burns off the soot, the extra soot in the filter. Now, I'm going to show you a little video clip of how both of those work. First, here comes the exhaust, the carbon, the O2, the nitrogen oxide, and it goes in there and gets collected by the filter. We have the oxidation is happening right there in the catalyst, and it increases the heat enough for the most part that it goes through, and then it does another oxidation chemical reaction, and out it goes as NO and CO2. Now, the same thing with an active. It starts out the same, as you'll see. Here comes the exhaust coming in, the carbon and the other parts of the exhaust. And pretty soon you'll see this fuel that we've injected come in, just hydrocarbons. And that creates a chemical reaction there that increases the heat dramatically and goes through and it cleans up the extra soot that's in the filter. So that's how it works. It's pretty much transparent to the operator. The only thing that he'll know that an active regeneration is going on most of the time is there'll be a little light that lights up on the dash that tells him it's happening. So that's how that works. Cooled EGR. They've used EGR in automobiles since the 70s. So it's not a new technology, but cooled EGR is a little bit of a technology change. The variable geometry turbo that's on there, that's used to maintain a correct pressure differential so that the exhaust EGR flows the way it's supposed to. The EGR cooler, some of the exhaust gas is pulled off the engine, it goes through that and cools it before it comes back into the cylinder. And then this control valve controls the amount of EGR that's added back in. And that's all controlled by the ECM. It's got tables. In the meantime, air from the turbo goes through a charge air cooler to cool it down. And remember, you go back to that chart where they cross, the cooler you get in there, you reduce NOx. So that's why Cool EGR is a really good NOx reducer. And essentially it goes in, and the exhaust gas that's in there is a placeholder instead of oxygen, which helps reduce the combustion temperatures, and it also absorbs heat during the combustion process, further reducing the exhaust temperatures coming out, or the in-cylinder temperatures. And runs through lower peak combustion temperatures, therefore lower NOx. SCR, selective catalytic reduction. This is, as I said, this is what we've been using in Europe since 2004. How it works, it's a little bit different. It's also a NOx reducer, by the way. So how it works is, as the exhaust gas is coming out, a bit of urea, diesel exhaust fluid, which is urea, is injected into the exhaust pipe, and it decomposes in here to urea. It goes through chemical reaction here to change, to get rid of NOx, and it comes out water, and I forget what the other one is offhand. It also has a slip catalyst in here, because sometimes some of the ammonia gets through the SCR portion of this without being used, and in order not to have an ammonia smell come out the back end, the slip catalyst will clean that up. As you notice, there's tank heater lines. There's a pump that's controlled by an ECM usually. The reason for all the heater lines and so forth is because diesel exhaust fluid does freeze at about 11 degrees Fahrenheit. So in the wintertime, you got to have heaters to keep that from freezing. Variable geometry turbos. There's a number of different types of variable geometry turbos. This type has a single sliding sleeve that I'll show. This is a video I'll show you. It's right there. Some of them, these vanes that you see in here, actually are all connected together, and they kind of open and close like that. Some engine manufacturers use that. Some engine manufacturers will use two turbos, a small one and a large one. Small one starts out, gets the boost built up, and the large one takes over. The variable geometry essentially acts as a small and a large turbo all together. So let me run a video to give you an idea how that happens. It'll start turning, and then you'll see a cylinder slide in, and it speeds it up, it spins it up faster that way because it restricts the flow, and then open back up for higher flow. Crankcase ventilation. We use a coalescing filter. I'm not sure what the other engine manufacturers are doing with this. I'm guessing some of them are also using similar. They're probably, in some cases, doing a closed loop and bringing this blow-by gas back in prior to the turbo. We use this, and we use it in an open, it can be used open or closed, but we use it at open. Blow-by gases come in here, they go through this filter, everything's cleared out of it, drops back to the crankcase, and then the only thing that's exhausted out is that air that comes through there, and it does a wonderful job. The only thing this does do is there's a filter inside here, and it is an added maintenance about every 2,500 hours or so. You have to change a filter. So let's take a look at, there's several different scenarios here. Tier 4 interim. This is Tier 4 interim for those engine manufacturers that are using SCR. Similar slide as I showed before with urea, a doser. It doesn't have all the heaters and that kind of stuff. It has a NOx sensor here, a temperature sensor here that's used to send back to the ECM to be sure everything is working the way it should. When you're doing this, and you go back to the particulates and the NOx on one doing versus the other one going up, one going down, what you end up doing with this type of system is you're actually tuning the engine to clean up the NOx inside. In other words, you're increasing cylinder temperatures to tune up the NOx, then asking the SCR to clean up the NOx that's coming out of the tailpipe. One of the things that does is it's your consumption of urea goes up. Consider the more NOx coming in, the more urea it takes to clean them up. So it can be running 5, maybe even as high as 8% of diesel fuel consumption. So if it's, you're using 100 gallons of diesel fuel, you'd use between 5 to 8 gallons of DEF in this type of format. If you look at the other way for Tier 4 is using a diesel particulate filter, cooled EGR, and variable geometry turbo. Essentially, we've talked about this, but here's our air filter. There's a temperature and barometric pressure sensor there. Goes through the turbo, here's your cooler, valve, and so forth, and then it goes through an oxidation catalyst, particulate filter, and then out. And in this case, you got some temperatures and some pressure sensors here that measure all of the different things that need to be measured and make it work the way it's supposed to work. And what we have found with this system, we're seeing up to a 5% improvement in fuel efficiency for Tier 4 over Tier 3, which is, over a period of a year, with the size of the fleet you got, it can be a significant savings. If you look at Tier 4 final, this is the presumed Tier 4 final solution. You'll see with those engine manufacturers that use the DPF and EGR and so forth, what they've done then is added the SCR version to clean up that extra 45% drop in NOx that you need to do. Those that started out with this first will end up looking like this at Tier 4 final. One of the reasons why we chose this way, we think it's a better way, lower cost long term, is that we didn't want to go SCR and then have to tear all that out, put in the DPF, EGR, et cetera, and then put SCR back in. Didn't seem to make a lot. Just to give you an idea of who's doing what, engine manufacturer-wise, this is for the 4-cylinder kind of technology. This is cooled EGR and after treatment, and the folks that right now that are doing SCR. As I said, there's mostly European folks. You got Deutz, some of the Japanese over on this side. You got us and Deere and Caterpillar, as usually JCB, Perkins here. When you go to the mid-range kind of product, 6 to 10 liter product, it's pretty much the same. You pick up, in this area, you've picked up Scania over here and Volvo Penta. They're loose engine sales, but Volvo Construction is over on this side, which is kind of strange, but why they've chosen to go different paths with different engines, but that's what they're doing. And then heavy duty, we've added a player here in Komatsu, and then Deutz heavy duty is over on this side, where before they were over on this side. But that's kind of what we see happening with the various engine manufacturers and which solution they've chosen. So it really kind of is interesting, and at the end of the day, you're going to end up with the same thing anyway. And it's just, some engine manufacturers have done the cool EGR DPF the first time, others have done SCR. Give you a little bit of commercial for us right now. Sorry. This is our product line for Tier 4 interim. We've got a 3.3 liter in natural, turbo, and after-cooled, and then electronic. Kind of horsepower brackets they all fit in. So this is kind of represents the lower end of our product line. From there we go to the 4.5 and the 6.7 under 174 horsepower. These are the horsepower ratings for both of them. And when we get into the 174 and up, which requires most of the work, is again 6.7 above 174 and a QSL 9 with those kind of ratings. Heavy duty. This is a new engine replacement for our QSM 11. And then the QSX 15 and those kind of ratings. And then the higher horsepower goes from 751 horsepower up to about 3,500 horsepower. So it's a full product line offering, all the way from the smallest to the largest. It's interesting that we haven't finalized what our interim solution is going to be for this high horsepower stuff, but what we're looking at pretty seriously is actually SCR, because of the fact that it's only here in the U.S. SCR is probably I wouldn't say the easiest to put on, but certainly it's probably the easiest to take off if you're not doing anything else out in the rest of the world. You know, we won't put a certified product anywhere else in the world, so if our certified product is SCR, then if you want to decertify, if you will, to use elsewhere in the world, that's probably the easiest thing to do, is to take it off. So, been through all that, a lot of stuff happening. None of it cheap, I'll say that, but a lot of stuff happening. Air quality is going to be immeasurably better. I mean, dropping 90% both NOx and particulates is a huge drop. It's really getting down to near zero emissions coming out of these engines. In fact, some people say that we could take probably a couple of truckloads of these engines and take them out to Los Angeles and fire them up, and the exhaust coming out would be cleaner than the air going in. So let's talk about how that impacts the customer. And as I speak to the customer, today I'm kind of talking about airline people. Are most of you airline people, or are you some of the OEMs? Okay. Engine manufacturers? Okay. Well, this is kind of aimed at the airline people, the end user customer, if you will. Right now, most of the fleets out there are from anywhere from Tier 0 to Tier 3 at the airlines, and quite a wide mix of them all, because for whatever reason, the airlines tend to keep their equipment for a long time. I live in Atlanta, and I can remember a year and a half or so ago, I was over at Delta at their JSC facility, and they had a bunch of old equipment sitting out there that was they were selling off. And I mean, some of this equipment was from 1940s. That's, and I don't think that's unusual with the airlines. I think they keep it for a long, long time. So, wide variety. What I think, though, is that Tier 4 interim is going to actually have a greater impact on the airlines than all these other three-tier changes put together, because there's just so much technology that has to be thrown at the engines to make it work. And by the way, I will say that when the EPA set the regulations for Tier 4, they did it knowingly forcing after-treatment technology. They felt that stuff is out there, we ought to be using it. And what you don't have available yet, you certainly should be able to design it and put it together. So, areas that are going to be impacted: your acquisition costs, maintenance, fuels, lubricants, fleet operations, equipment performance, training. I put TPM down here. That's really, it's a transition program for equipment manufacturers, and I'll cover that, but that's really aimed at the OEMs, not the end users. But I want to share that with you because you need to be thoughtful knowing that that's there and make sure you order the right things for what you need. Okay, acquisition costs. There is probably been no period previous to this that there hasn't been a greater opportunity to integrate the engine and the machines as there is for Tier 4. All sorts of changes. In some cases, equipment manufacturers are having to go in and actually re-engineer chassis sizes and so forth because of all the space claim required by all this after-treatment and that kind of stuff. And electronics, we've got some of the most, well, certainly by several major steps, the ECMs that we're putting on now are a lot faster, hold a lot more memory, they're a lot more powerful than what they ever had before. We can do a lot of work and connect in with the equipment manufacturer stuff and do it through our ECM as opposed to having several different control modules around. So there's a lot of that work going on. And there's going to be improved fuel efficiency. There's going to be after treatment to reduce exhaust emissions. And as I said, Tier 4 is like 02 and 07 combined. There's going to be increased cost, and certainly that's going to vary by those horsepower brackets that we saw earlier. And because this is the most stringent regulations, this is going to probably be the highest cost increase, engines in this range. And there's going to be changes by the equipment manufacturers to accommodate the radiator sizes and all those kinds of things fit into this as well. So those equipment manufacturers that take the time to do the best integration, we've done our job integrating the engine systems, and they are doing their job integrating the machine-to-engine systems. And those that do the best are probably going to, at the end of the day, have the best fuel economy improvements, because it's been designed in that way than those that don't. Also, local and state emissions are going to have influences on purchases. Not so much, Tier 4, what the Tier 4 stuff does to the cost of the engine, but how many different pieces of equipment you're going to have to buy and where you put them, and so forth. Just as an example, California in-use regulations. Even though they've been temporarily put on hold, and we're not really sure when they're going to come back, I guess there's a slim chance they might go away forever, but I wouldn't count on it, knowing California. But that's the kind of thing that's going to drive airlines where I'm going to have to buy a certain number of Tier 4 to put out in California so that I can meet the in-use regulations as they come back. They haven't given us a date when they will come back. I'm guessing that when the economy starts going again, they'll come back again. And having said that, why put Tier 3 product when Tier 4 product is available on anything new you put into California? You might as well just go ahead and put the Tier 4 stuff in right at the upside, even though the regulations aren't in effect right now. But when they do come back, you'll be halfway there with your fleet to be meeting those. Because once you hit Tier 4 on California, you don't have to do anything further with that piece of equipment. That's done from an in-use regulation standpoint. Fleet operations, manage global equipment infrastructure. As I said, ultra-low sulfur isn't available all over the world, so you can't put these engines all over the world. So you have to be a little bit thoughtful about, take my Tier 4 equipment, I got to keep it here or in Canada or in Europe someplace, or even over in Japan. If I'm moving stuff around, I can do that, but I certainly can't take it and send it into China, or there's another story about that altogether, but or anywhere in Africa, or a lot of places in South America. Can't do it. So it's something that's going to impact how you folks manage your fleet. Certainly, I think some things that are going to happen are, as you put Tier 4 interim units in California, some of the stuff that's in there now you may be taking out. Now maybe those Tier 2, Tier 3s would be great for China or for some of those other places for quite a few years to come. So that's something. If you have, if you're buying any equipment that has engines that shows the SCR path, infrastructure for the DEF support. That's both within the fleet itself. How are you going to manage that infrastructure within your fleet? And also, how are you going to manage that with your suppliers? Do you have a supplier? You've got to find a supplier and make sure you put all those things together. So that's kind of a two-level type of thing you got to look at. Extended idle periods. I see that quite a bit happening in equipment, GSE equipment. The unit will sit there and idle all day, particularly in the wintertime. That's not very conducive to efficient diesel particulate filter operation. The engine is producing more. It's lower temperature, so it's producing more soot and so forth. And that means that there'll be regenerations will increase because of that. You need roughly 300 C, 575 for a passive regen. An active regen can get as high, exhaust out of the DPF can be as high as 1100 degrees. It's pretty hot, so you got to be careful with that. But this could be an issue on how you have your equipment when it's sitting in between flights and so forth. Now, there's ways to mitigate that 1100 degrees. There's diffusers that you can put on the end of it, on the end of the exhaust pipe that drop it really quick. And really, 1100 degrees Fahrenheit really isn't much different than if you have an engine running at full power. just a 2 or 3 engine a day standard, it's going to run about that kind of temperature. The difference is, that's at full power, then that means that machine's working, doing something. If this piece of equipment decided to do an active regen while it was sitting stationary, you're still going to have that 1100 degrees, so it's something you got to watch out, people walking around it, those kinds of things. Yes?
I haven't seen this myself, but I heard tell that sometimes you get flames coming out of the exhaust pipe during some of the regen process.
We don't. No, we don't have any flames coming out the exhaust pipe. There's no place in our system where there's, once it leaves the turbo, there's no place in the system, all the heat, where there's any open flame. Now, and I will say, well, I'll get to that in a minute. There's some of these systems that have burners on them to increase the heat, a little spark plug, and it fires them off, and I'll get to that. And that's primarily CAT that does that. But yeah, you got to be that might be a little bit more of an issue there, but I've never heard of any of ours having flames coming out the back. There's nothing there that's combustible to the point that would cause open flame. What we have happen all the way through that system is chemical reactions, not an open flame, fuel burning. Now, I think I've heard of that occasionally on cars, but that's a little different system than what we have on these. What this is, we can go into our ECM and pull up a duty cycle report on an engine, see how it's running in the various, this is the percentage of torque, this is the RPM, and you see a lot of zeros over there, so it's not running in those areas. You see 5.5% here. This is probably a startup kind of thing that causes that, but where you see most of the operations are out here at, well, between 1950 and 2080. This is a 2,000 RPM engine, and that's where the GPU runs. So it says there's an awful lot of time spent running somewhere between 0 and 10%. So it's running at idle, or at a high idle there, really effectively no load on it. 45% of the time it's running between 10 and 30% torque. It's in that range. And then you got it 1.8% of the time, 30 to 50. If you looked at this, and you'd say, this one's going to be a hard one to make the DPF work efficiently. So the first thing you might want to consider on this is, how do I reduce that right there? How do I take that time out of the system? That would help with good, efficient DPF operation. I know, it's going to be a kind of a culture change, if you will. I think in a lot of places, as far as shutting down the equipment, when it's not in use. But to make the DPAS work well, and even for that matter, to make the SCRs work well, there's got to be heat. It's a chemical reaction, and the higher the heat, the better the reaction. Yes, sir?
What are you saying, that emissions testing will scan the ECM to determine compliance?
No. Nope. There's nothing like that going on today at all. What we have to do is figure out how to make this work better. Work with the OEMs and say, okay, this engine, this is a 220 horsepower engine. What would happen if we put a 180 horsepower engine in that machine, same machine, all right? Okay, now you've just moved up in the duty cycle range because it's going to still use the same amount of horsepower, but your available is less, so you've bumped it up into that 40% and higher probably duty cycle. That's one of the things that we can look at. What about just putting in, we've got all the electronics in the world on these engines and equipment now. Why not put something in place that after that thing is sitting at an idle for 15 minutes, as long as, and it can tell whether it's hooked up to the plane or not, as long as it's not hooked up to the plane, if it's sitting there 15 minutes, why not just shut it off automatically? Those kinds of things is what you're looking at. This is more to make the emission systems work better, more efficiently, And that's going to save money for you folks. The better it works, the less active going on, the less DEF being burned, and for, frankly, DEF, when it burns, there's a tank and it runs out. Somebody's got to come out and fill it back up again when that happens. So there's those kinds of things. You need to think about that a little bit. Maintenance. There's some new maintenance, a little bit of revised maintenance going on, and this probably isn't a complete list, but it's what came to mind after I got some creative juices flowing. But crankcase filter, for us that's going to be $100 or a $2,500 interval. I haven't seen any data on the other engine manufacturers. Do they have one? And if they do, what kind of intervals they have? But certainly they know what they are, and if you have questions about that, they should be able to help you with that. Fluids. We talked about fluids. Ultra-low sulfur, low ash oil, and we'll talk a little bit more about that, and DEF fluid. When you use ultra-low sulfur diesel, I have another section, and I'll just give you need to use a low ash oil. That's in the U.S., it's a CJ4 type. In Europe, it's this ACEA-E9 type of oil. And I'll cover it more when we get to that. Ash cleaning in the DPF, that's what really, when you do a major cleaning where you actually take the brick out of the DPF and you do a lot of blowing the air to get the main stuff out, put it in the oven to cook it for a while, you're getting the ash out of it. And that ash comes from the oil. And it's not, it doesn't, you can't get rid of it by any type of chemical reaction. You just physically have to clean it after a while. So it's right around the 5,000 hour. I think the EPA says we have to meet at least 45. Right now, we're looking at probably 5,000 hour. And then just to give you a corollary, we set the automotive cleaning cycle at about 250,000 miles when we first came up with our DPF. And what we found is, as we got to 250 and started pulling some out to look at them, they were really clean. We're now at, I think, 350. So we bumped it up. It wouldn't surprise me before we get all said and done and a little more experience behind us, we'll bump it up to 450. Those trucks they very seldom do active regens on trucks. They're running down those highways. There's a lot of passive stuff going on, continuously, but very seldom do you do active. Air filter, the new air filters we've got are going to be equal or, in fact, even some increased change intervals. So very likely you won't have to change air filters as often. This is a pretty easy environment for air filters anyway on the airport tarmac, so it's all right. If the engine after treatment includes a burner, then you got the maintenance on the spark plug. Another thing, you need to fix problems that can contaminate the exhaust system quickly. The reason is things like a turbo seal where oil gets into it, or exhaust leaks between the engine and the DPF. Coolant leaks could get into the exhaust, or a head gasket or something like that. If you let those things go, those things can go in and ruin a DPF. And those things aren't cheap. I'm going to guess a DPF in the 174 to 751 probably varies from maybe $3,000 to $4,000. So it pays to, if you see a problem like that, get it fixed right now, because it's going to save you money. Performance. Performance is equal to or better than Tier 3, up to 5% fuel economy, equal or improved horsepower and torque. More responsive, the VG Turbo is much more responsive than the older turbos, so lower noise, longer life exhaust system, and the reason we put that in, everything is stainless steel in the exhaust systems now to put up, to handle the heat and everything else, so those exhaust systems last a long time. Here's some information that I want to put up. This is based on a lot of the repowers that we've been doing and running and putting out in the field to get test hours on the Tier 4 product. In many cases, we put the machine out and there's a sister machine with the Tier 3 engine in it and this repowered machine with the Tier 4 interim. This is what the people are saying about them. More responsive with improved machine productivity, cleaner and quieter running. They haven't seen any black smoke at all because that particulate filter pretty much takes care of it. It's just really, and it's a really good muffler, as it turns out. So you don't really need to have a muffler on the machine anymore with the DPF filter. So far, it's been equally as reliable as a Tier 3. Intervention-free regens. Now this higher fuel economy, this is something that mostly construction equipment, which is different than GSE equipment, different duty cycles and so forth, but a lot of this will carry over, and the better we get with the OEMs to make these things work effectively for everybody, and some changes, in how they are operated, I think we'll get to these same kind of things. Certainly, efficiency, this, and this. We can reach those kind of things with GSE equipment. But we've had just a lot of very positive responses on these engines. Fuel and oil requirements. Tier 4 engines, as we figured it out now, they're ultra-low sulfur and low ash oil. High sulfur fuel will follow the after treatment. 3,000, and that's in the lower side. If you get into the heavy duty engines in that 750, it'd probably go up. And this wouldn't be considered a warranty failure if you were running higher sulfur fuels in it. Now, if you by mistake put some 500 in, it's not going to damage it that quick. If you go right back to it'll clean itself out, and the regens will work and clean itself out. But if you continuously put 500 parts per million fuel in there, it's going to take it out. One good thing, US LD is backward compatible to the older tier engines. So you got those Tier 0s or Tier 3, they can use this fuel. So from a fuel standpoint, you can get down to one fuel for your fleet. And I think that's good news, I think, for everybody. Where you have to be careful is with the oil. And I've got a chart to show you what I mean by that. You can run up to B20 biodiesel if you're running biodiesel. We've done the testing, and that works okay. If you're running engines with SCR technology, use a quality pre-mixed diesel exhaust fluid. And it's available. It's pre-mixed. It's about 32.5% urea to deionized water. You need to also be careful on your storage temperatures and length of storage. They do have a shelf life. Higher temperatures cause that shelf life to drop pretty dramatically on DEF. But if you're below 80, you're probably going to get somewhere between 6 and 12 months shelf life out of it. If you get up above 100, you could drop easily to 2 months as far as temperature. So you need to, if you got enough of these, you'll be, that stuff will be flowing through, or you'll never sit that long anyway. But frankly, I don't see you're going to have very many of them to start with. I mean, I don't know anybody that's going to go out and completely replace their fleet with Tier 4 product. And with the economy as it is, and with increased costs on buying this equipment, I would expect that you'll be fairly selective on what you buy and where you put it. With, frankly, probably most of it going to California, or there may be some other non-attainment areas that you might want to look at. So that's, don't try and mix your own. we've had some truck companies that have tried to do that. They just use regular tap water. Deionized water is what they use. And you can get calcium buildup if you're just using regular tap water, and that's just as bad on the DEF as a high sulfur going through the DEF, or I'm sorry, the DPF, or whatever. So it's best to let the people, somebody that's got a certified DEF fluid, and there are certified fluids out there. Here's a chart that shows the fuel type and the oil type. low sulfur diesel 500 ppm, and ultra low is 15, less than 15. This was the current oil. This is a high ash oil, and ash is in there, as I said, to offset the acid buildup from combustion. So you got higher sulfur here. That works just fine. Now, if you ran CJ with low ash, it would run, but your oil drain intervals would be dropped because you're starting out with a lower amount of ash in a low ash oil, and you got a lot more sulfur in this oil. So that additive is going to deplete a lot faster, so you drop that. Now, with ultra low sulfur, low ash, no sulfur, that works really well, and the added benefit there is you don't lower your ash cleaning interval on your DPF. You don't truly reach that 5,000 or 350. But if you run a high ash oil in here, it's not going to hurt anything other than the fact that your ash cleaning interval is going to drop. And you'll have to do it more frequently. And an ash cleaning, you got to have special ovens and all that kind of stuff. But a round figure, about $500 to do an ash cleaning in a DPF filter.
I'm not a technical guy, so a lot of this stuff is full over my head. What happens if you run JP8 on these engines?
That's a high sulfur fuel.
You don't run it?
No.
Just on a regular basis?
No. Now, this doesn't help you a whole lot, but Wheel will continue building Tier 3 engines for the foreseeable future because of the U.S. military. You know, they've got their one fuel battlefield of JP8, and so we'll continue building that Tier 3 product because it doesn't care whether it's got high sulfur or not. That engine will run with anything. So that's going to drive us, and in other parts of the world. That's our other non-attainment areas of the world. I mean, where there's no ultra low sulfur or there's no regulations, the Tier 3 engine is going to be available to all of the equipment manufacturers for exporting purposes and so forth. Or maybe even to sell to you if you know that's going to be placed somewhere where there isn't any regulations and it's going to sit there its whole life. That's certainly an option. Because one thing to keep in mind is that the engine cost is going to be lower, so therefore the equipment price is going to be lower. I just bring this back to remind people that it's all over the board, all over the world. Sorry. Perfect place for Tier 3 engine. Another great place for Tier 3 engine. Tier 4, Tier 4, Tier 4 over in there. Training. Something else that's going to change. There's dash lamps. There's going to be new dash lamps for Tier 4i, and I'll show them to you. I've got them here in just a minute. So the operator needs to understand what those are and what to do when they come on. They need to be familiar with passive active regeneration processes so nothing surprises them when it happens. There's an inhibit switch that's going to be available so that you can stop that type of, if you feel you're in a place where it's not safe to do it, and you can do it, pull it over later somewhere else and let it happen while it's sitting there. And you can also use that then as a manual regeneration, that same switch. From a technician standpoint, needs to understand this enough, not necessarily troubleshoot it to be able to fix it, but troubleshoot it to understand what the problem is. All of our troubleshooting technology and our tools that we have today are fully capable of troubleshooting Tier 4 product today. So, I don't know if you have those things, but certainly we're capable of doing that. Make sure that nobody's changing these emission devices. This can get expensive. $2,700 per unit per day from the EPA. And at the OEM level, about $32,000 per unit. So EPA so far hasn't really been out auditing too much. But think about the fact that Tier 4 and on-highway 2010 are kind of the end of the line for this massive of type emission regulations. So those people aren't going to be doing that much anymore. And they're moving, I don't know, something like 30–40% of their people are going to be moving into the audit side, and they're going to start doing more of the auditing as we look out in the next number of years. So just, you know, you may not get caught today, but tomorrow, just, you know, be careful. We talked about these. These are some new maintenance schedules that we've already talked about. The dash lamps. These lamps, the icons are actually from the Association of Equipment Manufacturers standards. They developed them, and they are mandatory in North America. They, I guess, aren't overseas, but I imagine any U.S. manufacturer is going to be doing them, and any European or anywhere else will have to use these if they're shipping equipment into the U.S. That first one is a DPF lamp. It indicates a need for assistance. This little thing right here kind of indicates it's plugging up. This is a temperature. It's called a HEST lamp, a high exhaust system temperature. And that comes on when an active regeneration is underway. It doesn't mean the operator has to do anything. All it is just a lamp to let him know what's going on and keep going. He doesn't have to stop the vehicle or anything. He can keep operating, doing whatever he's doing, and let it go. Check engine lamp. This is telling him that normal operation is no longer possible. There's some service that needs to be done. And stop engine lamp, this says, well, there's some system damage that has occurred or is imminent, and you better stop that engine pretty quick or else you're going to cause some serious damage. Here's the manual regeneration switch. You push start, and it manually initiates an active regen while the equipment is parked. Most of the equipment, the way the ECM is set up is that it won't do an active regen under certain miles per hour. But you can manually override that here, and it probably is going to be a little different than that for some of the off-highway equipment. I haven't seen what all of those little things are, and we're playing with some of this as we speak in some GSE equipment on where do we want to set those actually and so forth. So that's going on. A regeneration, the inhibit switch, that's this bottom part, stop. You can manually turn off an active regeneration if it's in process. You can prevent one from happening, and really you need to activate only when the high exhaust temperature may cause hazardous conditions. If the thing is parked out by an aircraft and it goes into active regen, the hazardous condition to me isn't so much the airplane as is the people walking around it, depending on where the exhaust is pointed out. And particularly if you don't have any type of mitigating temperature device on the end of the exhaust. It could burn somebody's leg or something like that. So don't do it a lot. It's going to end up resulting if you always shutting off the active regen, eventually that filter is going to plug up. Okay, we have a simulator just to give you an idea. Those are the different lights. It's going normal operation. These lights aren't on, by the way, but this is just, and I'll just go to the next one. Okay, I haven't seen that play around, but normal with passive regeneration. Normal operation, it's going into passive regeneration. That's why you're seeing this thing going back and forth. It starts getting up and it's cleaning it. There's no lamps on, nothing the operator needs to do. Let's go to an active. Normal operation, it's an active. The HEST lamp will be on, there it is. And really the only thing the operator has to do is just use caution at this point. Normal without active regeneration. There's been no regeneration going on. DPF is moderately full. You can see it's somewhere up in there. You'll see a slight torque derate. Enough that the operator will feel it, but not enough to cause him to interrupt what he's doing. The DPF lamp is flashing, so they need to perform a stationary regen as soon as possible. Still haven't done a regeneration. DPF is almost full. Now we get a moderate torque as well as a speed derate. Still flashing. Here comes your check engine light. You need to do something right away. And that's pull over, stationary regen, get it done, but you got to do it soon. And there's your switch to do the, it tells you that's what he pushes. Full DPF. Severe derate. Now, it's not going to shut the engine down, but it's going to allow him to get back to a service department or something like that, but it's not going to allow him to continue operating. Red light's on. Way up here, severe. Stop engine immediately. Contact Cummins to get a service technician out there, because they have equipment that they can maybe do a derate and get this going. It may be that it's been too late and now they got to pull it out and see if they can get it fixed by running a cleaning process and put it in an oven. And it may be too late where they have to replace the DPF brick. Yes, sir.
So you're saying in the GSE world it's going to be set up this way in the equipment, that engine?
Well, you're going to see all of these lights. There can be some, we're still playing with what actually happens in each case. At the end of the day, though, we want to have enough happen that this never happens. We need to get somebody's attention enough that they know what to do.
I don't know any other way to put this other than in our world, we have overcome stupid.
I understand.
And it's
Yeah.
tough to do.
Yeah.
I can see that costing all of us no money.
Yeah.
Just for the upfront cost plus
Yeah.
all the damages.
You know, you always hate to shut an engine off because you never know, do it electronically if you get to a certain point, because you never know where somebody is in their work process. We're going to be we've got some beta engines now that are going into some GSE equipment. We're going to be playing with that. We've got an alpha engine, for a 4-cylinder, going in this summer that we're going to be getting out to one of the freight carriers. And we want to understand this, and we're probably going to be playing with it and reformatting and doing a number of things to make this thing work so we want to protect the equipment for your sakes, but at the same time, we want to be able to do it in your environment. And that's a big job, but hopefully we can come up with something that makes sense for everybody.
Yeah, there's something you could do to make it go into like a limp home mode,
Yeah.
where it's totally operational.
That's this one right here.
Possible damage.
Yeah, that's this one right here that we'll go, it's kind of a limp home mode. And it hasn't done enough damage that you couldn't, get it somewhere and shut it down and then have somebody come check it out with our inline adapter, full-blown tools to see if we can't fix it.
At this stage, a manual regen is sufficient to bring it back?
Probably not. It's something you could try, certainly. But it's, as you see, from a DPF loading standpoint, it's getting into the red here. And a manual regen may not quite be enough. Certainly, if your operator sees that he's that far, limp it into, a service area or something, and the first thing you'd want to do is put it into manual regen to see if it takes care of it.